Chem 106, Chapter 21, Nuclear Chemistry, Lecture 1. Nuclear reactions involve changes to the nuclei of the atoms, and so we call these particles in the nucleus nucleons. And so a proton is represented by this symbol, and a neutron is represented by this symbol. Now, this is different than when we talk about isotopes, but let's, back up here. And atomic number, of course, is the number of protons. You learned that a long time ago. And the mass number is the sum of the number of protons and neutrons. Learned that a long time ago when we talked about isotopes. But notice the symbol as a nucleon for the proton and neutron. That's different than what we did when we talked about isotopes, where a proton was simply a P plus and a neutron is an N0 and an electron is an E with a minus superscript. So keep in mind which context we're talking about when we do these particles. All right, so then a nuclide. Just the word nuclide refers to the nucleus of an atom without regard to the energy levels of electrons and all that, just the nucleus here. So a radionuclide refers to a radioactive nucleus. Now that's different than saying a radioactive atom, because with the atom now you are taking into account all of the energy levels with their electrons and all. But a radionuclide is just the radioactive nucleus of the atom. And so atoms themselves containing radionuclides are called radioisotopes. On this exam, terminology is going to be very important. So make sure you know the definitions of all these terms and keep them straight in your mind about what is what. All right, so a nuclear equation then is going to describe how a radionucleus is going to decompose, or a radioisotope, I should say, is going to how it decomposes. So radionuclides, of course, are unstable, and they spontaneously emit particles or electromagnetic radiation as they decompose, or decay is the right word there. When a nucleus spontaneously decomposes, and we'll call it radioactive decay, then we have these nuclear equations that we can use to represent the process of what's happening. So remember, with isotopes, you pronounce them as their element name and then the mass. So when we look at this reactant here would be uranium-238. Now, I know it's redundant to have the atomic number as a subscript along with the symbol of the element because those are tied together. But for complete isotopic labeling, we do use all three parts. So make sure you keep that there, that we need all three parts. So what will happen then is with uranium-238, it'll spontaneously undergo a decay and emit what we have as a helium nucleus. Because remember, we're only talking about from the nucleus here. We have no regard for the electrons and the energy levels surrounding the nucleus. All of these processes are nuclear in nature. So what's going to happen is this uranium-238 atom is going to emit 2 protons and 2 neutrons. And so those 2 protons and 2 neutrons are the equivalent of a helium nucleus. So as you can see, what's going to happen here is that the element, because it loses 2 protons, it goes from 92 to 90, which is thorium, and it's going to lose a mass of 4 because there's 2 protons, 2 neutrons, each having a mass of 1 AMU. So this is one common kind of decay where you eject from the nucleus a helium core. And so then that reduces the atomic number by 2 and the mass by 4. So again, algebraically, all of these numbers across this arrow, which is the same thing as an equal sign, they all have to be the same. So 92 protons on the left, 90 here and 2 here still adds to 92. A mass of 238 on the left, mass of 234 and 4 over here, which still adds to 238. So, just like any algebraic equation, all the numbers have to stay the same on both sides. All right, so let's talk about the types of radioactive decay here. So you've seen this helium nucleus that can be ejected. That helium nucleus or core is called an alpha particle. And so you should be able to use the lowercase Greek letter alpha when needed. So this is called alpha radiation, and so that's the ejection of a helium nucleus or core from the nucleus of the radioactive atom, and so its atomic number decreases by 2 and its mass decreases by 4. The beta radiation, that's the loss of an electron from the nucleus. Yes, I know electrons aren't supposed to be in the nucleus, but actually, neutrons are made of a fused product of a proton and an electron. So really, then when we talk about beta radiation, what we're talking about is the decay of a neutron. All right, and so the beta particle itself, the electron, has this symbol, 0 mass and a -1 on the atomic number. Because again, algebraically things have to add up, and then E, of course, for electron. But again, beta radiation is the loss of an electron from the nucleus as a neutron decays. And so let's look and see what that means then. For beta emission then, a neutron decays into a proton and an electron, because again, that's what a neutron is. That's why the neutron was just slightly heavier than the proton, even though really within significant digits value, they were both 1 AMU. But the neutron's slightly heavier because it's the fusion product of a proton and an electron. So when a neutron decays, it becomes a proton and a fast-moving electron, which is ejected. The proton stays in the core, but the electron is ejected from the nucleus. So that's beta emission. Neutron decay, proton stays with the nucleus, but the electron is ejected away. Now, in a similar fashion, radioactive nuclei can do electron capture, so that an electron that is fast moving but strikes the nucleus of an atom can bond to a proton, becoming a neutron. And so we'll see, possibly about some of the effects of those, how beta emission and electron capture affect the atomic number, and so on. The third kind of radioactive decay is called gamma radiation, and that's the loss of high energy photons from the nucleus. So again, there's no change in mass and no change in particles. It's just the loss of energy from the nucleus. So that's really the energy. Whereas both alpha and beta are loss of real particles from the nucleus, gamma radiation is simply the loss of energy during that whole process. All right. Excuse me. With this, we can talk about radioactive decay chains, because usually a particle isn't just going to emit, or a radioactive nucleus is not going to emit just one particle. There's going to usually be several, and so we call these decay chains. So with an alpha decay, we emit a helium core, and that's going to cause the mass to decrease by 4 and the atomic number to decrease by 2. If we undergo beta decay, that's the emission of a fast-moving electron during the decay of a neutron. And so the mass remains the same because electrons don't change and the proton remains behind. But the atomic number actually increases by 1 because we did have a neutron which didn't affect the atomic number, but we've created a proton which does affect the atomic number and the electron which is ejected out. And then with gamma decay, then that again, we're just losing energy. So it results in a net loss of energy from the radioactive atom, but we don't affect either the mass or the atomic number in this manner. So there are a series of these. So that's what we call these decay chains, because there are a series of these. And there is a website that I want you to go to, and I want you to study it and see if you can make sense of it. Oops. There, and here is the website. And so it goes through decay chains, and talks about various series and all, and then it actually walks you through the decay chain of thorium-232, and so you can see how. And remember, gamma is not included here because that's just loss of energy. But if we have either alpha or beta decay, you can see what happens. So just as an example, with thorium-232, which is atomic number 90, if it undergoes alpha decay, it becomes radon, which is atomic number 88, and it loses a mass of 4, so it goes from 232 to 228. It can now undergo a beta decay, which, remember, that's a loss of an electron from the nucleus as a neutron decays. So we're going to gain a proton, so we go from atomic number 88 radon to atomic number 89, which is actinium, but you notice the mass didn't change. And if we undergo another beta decay, again, that's going to be a neutron decay, so the proton stays and the electron leaves. And so we again gain another proton, so we go back up to thorium, and we have not changed the number. So essentially, through an alpha and 2 beta decays, we go from thorium back to thorium, just a different isotope of thorium. So again, just for an example, if thorium-90 undergoes an alpha and 2 beta decays as a chain, then we're right back to thorium, not as an isotope, but we went from thorium-232 to thorium-228. And then again, thorium-238 is not stable, it's radioactive, and so it continues along the chain and does another alpha emission, another alpha emission, another alpha emission, another alpha emission, and then a beta. Then it can go either to another alpha or a beta, and then another alpha or alpha beta. But it's going to all end up at lead 208 anyway. That's the end result usually. That's where we find the stable atom, is at lead 208. So when these radioactive atoms just simply go through their natural decays, we usually end up at lead 208. So again, you can follow the pattern and you can do the calculations yourself to see how this works as a chain. Now, the much bigger one, so if we look at this is much better because you can see all kinds of patterns in this. But again, see where we're going to end up here is still at lead. Lead 207 is also stable. Okay, so let's see. And then there's uranium-235, which of the two isotopes, uranium-238 is not usable for nuclear materials or even nuclear medicine or anything like that. To power plants, to nuclear medicine, to bombs. It is uranium-235 that is necessary for all three of those things. And this is the decay chain that uranium-235 undergoes. Okay. But see, again, they're all here, just so you know, you can really go through all of this and see what happens. All right. So why don't we go back to the outline then and look at some of the possibility. How do we calculate this? Yeah, this is a good place for that. So what we need now are the lecture problems. And so when you get your lecture problem, number 1 talks about astatine 215. So astatine 215, remember the mass is written as a superscript, and astatine is number 85. So there is the complete isotopic symbol for astatine 215, and it's radioactive. It doesn't stick around very long at all. And what the question is that astatine undergoes 2 alpha decays and 1 beta decay. What is the final product of this decay series? Okay, so we walk it through stepwise, just like we always do. And so if we start with astatine 215, then, and actually let's clean that up a little. What we're going to do is let's do an alpha decay. And so that's the same thing algebraically as saying minus. And since it's alpha, we are losing a helium core. And so remember, in algebra, in chemistry, the arrow is the equals of mathematics. All right, and so we're subtracting. 215 minus 4 is 211. 85 minus 2 is 83. And so now you need a periodic table and look up what element is 83, and you will find that it is bismuth. All right, there's 1. So now again, 211, bismuth, 83. Let's do the second alpha decay. And we end up with 211 minus 4, which is going to be 207, and 83 minus 2, which is going to be 81. So now we need to know what element is 81. And when we look at the periodic table, we're going to see that it's thallium, Tl. All right. So now we have 207, thallium, 81, and we're going to have a beta decay, which is 0, E minus -1. Okay, and so with this, and actually not though, sorry about that. I'm combining symbols now. The nucleon type of the electron is E0 minus 1. So again, with algebra then, 207 minus 0 isn't going to change, but 81 minus a minus 1 becomes 82. And so on the periodic table, we find 82, and we'll see that that is lead. And so the end product of this then, 2 alphas and 1 beta, gives us lead 207. And so remember, the way we pronounce these then, whether you write this complete isotopic symbol or even just tell me it's lead 207, I'm okay with either way. But as long as you tell me the correct, real isotope of it. And so walk it through step by step. There's no reason not to, just to be careful with where the numbers go. All right. Going back to the outline then. All right, so nuclear transmutations. Nuclear transmutations are nuclear reactions resulting from the collision between nuclei or between a nucleus and a neutron. This is where, in the old days, really old days of the 50s and 60s, this might have sounded like science fiction. But it became such a reality because, remember, only elements up through uranium, number 92, are naturally occurring. Everything beyond that has been a result of nuclear transmutation. So elements 93 through now, at the time of this recording, 118, those are all human-created elements using the idea of nuclear transmutation. So they're all artificial elements. They don't exist in nature. They're all human-created. All right, so what we can do then is, of course, use an accelerator to do this. And so accelerating the charged particles, so either a cyclotron or a synchrotron or whatever we use, using strong magnetic and electrostatic fields so that we can guide the charged particles around this huge tube. Because remember, these particles are tiny. And so we use magnetic fields to control, because remember, electricity and magnetism are the same fundamental force. So if you put a charged particle into a magnetic field, you can control the path of that charged particle using magnetism. And so we can guide these particles around a huge tube that that is miles long. And we can accelerate it. We can make it go faster and faster and faster by manipulating the magnetic field that it's in. And so we can draw it along the path and make it go faster and faster. And then we can slam particles into each other, and we can study those effects and what we can make from them. All right, and so several of these, like the relativistic heavy ion collider at Brookhaven National Laboratory, or the Tevatron at Fermilab, or the Large Hadron Collider. This is the newest, biggest, promising collider, at least at the time of this recording. And that's at CERN, which is under the France and Switzerland border. It's right on the edge and crosses between France and Switzerland. So it's these things are underground because they're miles in diameter. And so the Large Hadron Collider that came online, I think, in 2009, and has been doing amazing things ever since. And the Tevatron at Fermilab was before that, some of the really nice stuff that came from that. But again, all of these things, and we can use nuclear transmutation to make new elements. And so synthetic isotopes, everything after 92, so 93 through 118. So these, a lot of them were created involving neutron collisions. But that's not the only way. We can also take elements below 92 collide them with neutrons and create synthetic isotopes such as cobalt 60. And so cobalt 60 is used in radiation therapy, very, very effective at treating that using gamma radiation emission from that. All right, so transuranium elements, so transmutation is the process, but the transuraniums are the ones that are above 92. And so I'm going to have to update this outline at some point because, yes, in 2012, finally elements 114 and 116 were recognized, but it's going to be at least sometime in 2017 or so before the International Union of Pure and Applied Chemistry officially names elements 115, 17, and 118. And one of the persons that had the most effect on this was Glenn Seaborg. He is probably the creator of the most number of transuranium elements. So everything from 93, up through the last one he did, which I don't remember. But now we're up to 118, which finishes period 7. So that's really neat. He died in 1999, and so then one of the newer transuranium elements is actually named Seaborgium after Glenn Seaborg, who did so much of the pioneering work to create all of these transuranium elements. All right, so now we go into rates of decay, rates of radioactive decay. Thankfully, this follows first order decay rates, so that makes it really, really easy to do the calculation then. But each of the radioactive isotopes has a characteristic half-life. And so remember that from kinetics. We did that, and it was one of the first topics we covered this semester. And so natural radioisotopes tend to have longer half-lives than do the synthetic radioisotopes. The synthetics tend to fall apart a lot faster than than naturally occurring radioisotopes. And the half-lives of radioactive isotopes can be from fractions of a second all the way up to billions of years. When we look at uranium-238, the half-life of uranium-238 is 4.5 billion years. And so let's talk about what that means then. Half-life, again, refresh your memory. That's the amount of time it is required for half the concentration of a sample to go away, whether it be chemical reaction or nuclear decay. Either way, the time it takes for half of your sample to disappear is called the half-life. And so remember, this is just a nonlinear decay kind of function, because you're going to lose a half, then you're going to lose another half, then you're going to lose another half, all the way, and you never reach zero because it's asymptotic. So hopefully you remember all of this from the kinetic chapter way a long time ago, right? And so for all of the uranium that started out on this planet 4.5 billion years ago, we are just reaching the first half-life of all that uranium-238, which, remember, goes down to lead. So the lead that's here and is steadily increasing, a lot of it came from the decay of the uranium that was in the soil. And there's lots of uranium that's in the soil all over the planet. It's just that most of it is uranium-238. Very little of it is uranium-235. And that's what's needed to do the nuclear reactions. But let's talk about radiometric dating then. The half-life of any particular nuclide is constant. And so if we want to determine the age of an organic substance, something that was alive, by the way, not just any organic compound, it has to have been alive at some point. And we can use carbon dating to tell how old it was when it died. Because as long as you're alive, you're consuming. So whether you or a plant or some animal or even plants that are turned into fabric, for instance, you can tell how old that thing is, at least how old it was when it died, by using carbon-14 detection, because of course when you die you quit eating and plants stop taking in nutrients and all that, so the amount of carbon-14 no longer increases. Because what we find is carbon-14 is created in the atmosphere through a nuclear reaction with an isotope of nitrogen, and that radioactive carbon falls to the earth, so it's in the soil, and so then the plants take up the carbon-14, and then those that eat the plants take in the carbon-14, and those that eat the things that eat the plants take in the carbon-14, and it's constant throughout your lifetime how much carbon-14 you're taking in. And so when you die, you stop taking in the carbon-14, and so what is there now is undergoing decay, and so you lose more and more carbon-14 the longer you've been dead. And so we can work backwards through the calculation and find out how old you were when you died, basically. Now, this does not work with things that have been very recently dead. We're looking at things that are hundreds or thousands of years old where we want to really know. And this will work all the way up to 50,000 years. So we can tell how old something was when it died all the way back to about 50,000 years. Because the half-life of carbon-14 is 5,715 years. So that's why if it's really new, there's still essentially all the carbon-14, so it makes it difficult. You know, you've been in lab, you know how the experiments have, a decent amount of deviation to them from what you expect to be the accepted value. And so even under careful conditions, if it's too new, it hasn't decomposed enough to give a reliable measurement to say how old it is. So if you get out to several hundred years or more, from anywhere from several hundred to almost 50,000 years, you can be pretty reliable about how much carbon-14 is there and roughly how old it is based on that. Okay, and when carbon-14 decays, it goes back to nitrogen via a beta decay. So it's created in the upper atmosphere as a reaction with nitrogen, and then it just goes back to nitrogen when it's done. All right, and so uranium, as I told you, uranium to lead dating has been used to estimate the age of the Earth, and that's approximately 4 to 4.5 billion years, based on how much uranium theoretically was there in the beginning and how much is there now in any given sample. So the age of the Earth is approximately 4 to 4.5 billion years old. All right, so calculations based on half-life. Again, you're very, very comfortable with it. And so the decay is a first-order process, so rate is equal to K times the concentration of the nuclide. And so then the half-life is going to be first order, T1 half equals 0.693 over the rate constant. And the integrated rate equation is the natural log of the concentration of the nuclide at time t over the concentration of the nuclide at time 0 equals negative KT. And so, of course, we can do this calculation. Before we do, though, let's just finish this last piece here on the units of radioactivity. One unit is called the becquerel, and that's abbreviated BQ, and that's the SI unit for radioactivity, and it's equal to 1 disintegration per second. Disintegration meaning some kind of emission, whether it be an alpha, a beta, or gamma radiation. But you're probably more familiar with the Curie, named after, of course, Madame Curie, who did a lot of pioneering work with radioactivity. Her research journals are still so radioactive that people can't touch them. So her journals are still kept in a lead-lined container because you can't touch them because they're still so radioactive, and they will be for quite some time. But at least her journals are there and preserved. But the Curie is an older but still widely used unit of activity, and that's, of course, 3.7 times 10 to the 10th disintegrations per second. And so that's a CI, the Curie. And there are others, too, how we'll talk about radioactivity in the next lecture. But the becquerel is the SI unit, and the older, more common, kind of that was used, sort of like the difference between a joule and a calorie. Calorie is still what most people recognize, but joule is now the scientific version of energy. But the becquerel is the SI unit, and the Curie is the more common unit. But let's solve another lecture problem involving radioactive decay and how much of a sample will be left. All right, so we need lecture problem number 2. And that says the half-life of cesium-137 is 30.0 years. How much of a 30 milligram sample of that cesium-137 remains after 76.0 years? Okay, so again, you remember the equation, ln of the concentration of Nt over the concentration of N0 equals negative Kt. But we can change this because what we're solving for, how much is left at some time. So we want N at time t. So N at time t is going to be equal to e to the minus kt times N0. Just like we did back in the kinetics chapter a long time ago. All right, so now, once we have this, we need K, and we weren't given K. We were told the half-life is 30.0 years. So T1 half equals 0.693 over K. So therefore, K equals 0.693 over T1 half, which equals 0.693 over the half-life, which is 30.0 years. And so that is going to give you a K of 0.0231 reciprocal years. All right. So now let's separately work out KT. And so that's going to be 0.0231 reciprocal year times the time. The time given to us was 76.0 years. Notice the units cancel out just like they should. And that's going to give us a value of 1.7556. All right, so now again, N at time t equals e to the minus kt times N0, e to the minus 1.7556 times 30.0 milligrams. That's going to e to the minus 1.776 is 0.172, 803, 529 times that 30 milligrams. It's supposed to be a 0. Okay. And that gives us a raw answer of 5.18 410 5872 milligrams. Okay, now working through, because we have to round this just like always. And so the numbers that we had that matter were the 30.0 years, the 30.0 milligrams, and the 76.0 years. All right, so when we did all this then, with the 30.0 years, that gives this as 3 significant digits, which coincidentally was how many it was in the raw anyway. 76.0 is still 3 significant digits, so we should have 3 here. So which gives us this. So then we're going to do an e to the minus blah, blah, blah. That's an inverse log, which means then the number of decimal places becomes the number of significant digits, which is 2. And this has 3. So our final answer out of this, 2 there, 3 there. So our final answer has 2. We draw the line there. So our final answer then is 5.2 milligrams. Because that 8 changes that 1 into a 2. So the result of this is 5.2 milligrams of the cesium-137 remaining after 76.0 years. This concludes Lecture 1.